te aroha o rata mai, haere mai, whakatau mai nā.
Tēnā rā tātou katoa takino. E tupu te karito wai hora kia tupu ana. Kei tēnei huihuinga, te kāhuitanga o te whakatairanga tia, whakeke nei ki runga te whakanui atara, tēnei ka mihi ake, tēnei ka mihi ake. Hara meira te maunga auraki, hara meira mai te wai paunama, haere meira kei koa tūra o tautahi, hara meira ki runga i te kaupapa, karangihi ai tātou te wahengarua mā tauranga, te wahengarua whakatairanga tia, te wahengarua ta mana ihi, te wehi, te tapu, te kāhui, ariki te kāhui, rangatira, ko tai mai. Kai te rangatira e Tim Ahorangi, e te Ahorangi e Tim Haramai. Nei rā tō tātou pirihiteni, a Melanie o tira te whānau, roto ngā hauepa, ngā mātāwaka, tatu nei ki tō tātou kaumātu, huri noa ki ngā pūkōrero kai karanga, whakatau atu ki a koe, pe te Ahorangi e Tim, tēnei ka mihi ake, nauma hara mai, piki mai kake mai, whakatau mai rā, tēnā koe, tēnā koutou, o tira tēnā rā tātou katoa. Kei aku i te wā. Kia ora tātou.
I tā iwi tēnā koutou, ko Bernili, tōka wingawa no Otatahi ahau. It's my pleasure. I'm delighted to introduce Professor Tim Bell, a computer scientist who I am proud to say resides in my area, in my neck of the woods, Otatahi, Waitaha. Tim leads the Department of Computer Science and Software Engineering at the University of Canterbury, and he has studied in many fields of computer science education. He's studied computer music and data compression. His project, Computer Science Unplugged, is widely used internationally and, as you've read, has been translated into over 25 languages. He's received numerous awards for his work in computing education, including in 2018, the Outstanding Contribution to Computer Science Education Award. He's been actively involved in computing education in the design and deployment, including the approach of teaching digital technologies in New Zealand schools. A colleague states, "What makes Tim rise above every other teacher that I've ever encountered is his personal values and qualities. He knows who he is and why he's teaching. Tim has a deep desire for his students not only to understand the material that's being delivered, but to love the learning as much as he loves the teaching. He's also known to play certain instruments with black and white keys." So please join me in welcoming Dr. Tim Bell.
Oh, kia ora tātou. I have never had such a humbling welcome. And I learned a bit about myself. Thank you for that. Wow, I'll have to find out who that colleague was that said that. It's a real privilege to be here, and again, thank you for such a proper welcome. Wow. Okay, so the topic that I've proposed to talk about is making sense of digital technologies and Hangarau Matihiko curriculum content, and I'm going to do that in about 40 minutes. What could go wrong? To cover my back, I've put together a Google Doc, which is far from complete, but you know how there's 3 talks you give, the one you prepare on the way, the one you actually give, and the one you give on the way home. So my technique is, on my way home, I'll be filling up this Google Doc with everything I wish that I told you, okay? And it already contains a few links to some of the things that I'll talk about. Since you brought up about black and white keys, yes, I play keyboard instruments. This is not me playing an instrument, but it is actually the main instrument I'm actually qualified to play is the pipe organ. And this is a very early one, and it's a really good example of technology because it's intervention by design. Someone has taken some ideas about pipes and wind and a bit of science and put them together and made something that we often refer to as the king of instruments, some of us. But as with any technology, you can't help but wonder if it could be improved. And if you are thinking of upgrading, you're thinking, actually, this could cost me 2 weeks of downtime trying to get the new system going. Maybe it's got new things in it that don't work like they used to in the old one. And one of the things that people say about computers is that you go to it with a problem, like I need to print this document or write this article or something like that, and in return it gives you 3 problems. I need to print this. Sure, could you just install this driver first? Not a problem. Could you give me a password while you do that? Not the one that you know, but the one that you used 10 years ago when you first set up this thing. Oh, and by the way, printer's not working, try again, which never works. So, and while I joke about these things, this is the reality, and I think the knowing laughter, nervous laughter indicates that some of you have had bad experiences with computer systems. And I'm a computer scientist, and I've come to the view that computer science is the science of manaaki when you're writing programs, manaakitanga. If you understand manaakitanga, you understand computer science. If you know how to hurt people, then you don't understand computer science. And a lot of the things you've used have been put together by people who know a little bit of stuff, but don't understand manaaki. Okay. Your mana has been pulled down by... Has anyone been embarrassed by software? I mean, I'm hoping this thing works because otherwise I'm in front of a whole lot of people going, he's a computer scientist and PowerPoint's not even working for him. Right? So, if you take nothing else away, the new digital technology curriculum is about manaaki, okay? But in the specific context of I am going to write a computer program and I am going to build up the mana of the person who's using it. I'm going to help them get their job done and not hold them up, not give them 3 problems for the one problem they came along to solve. And if you've got that attitude, you'll be great at that. And if your attitude is, well, we'll talk about that in a minute. Yeah, since Ototahi's had a good mention already, I thought I'd bring along the phone book for Christchurch. Which, now, does anyone know how to use one of these? You do? Okay, could you look up something for me? Is that all right? Yeah. So I'd like you to look up this number. 385 1024.
And it's D and D Rose, 254 Main Road.
385 1024?
Oh,
No. Good response there, yeah. Had me thinking for a minute there. So, so I have and some of you may have heard this story before, I have a friend who's a little older than me now, but when he was a teenager, there was a girl in his class that he really liked at high school. And he was quite shy, and he didn't know her surname. And he was too shy to ask her. And so somehow he found out her phone number. And being shy and a teenager, on Saturday morning, he took the phone book. And, you know, motivation is everything, isn't it? And started, and her name was not Aardvark. And so on Sunday afternoon, in case you're wondering, he found her name. And actually, after I told that story once, someone asked me what happened next, and I had to go back and ask him, and it turned out he was too shy to talk to her anyway. So, but it was a special weekend looking for her name, or maybe just creepy actually. But and of course, we have much more automated ways to do that now. She's still looking, gosh. Yeah. Yeah, there's plenty of characters in it, but it's not a good story, really. Is it? Yeah. So, But what he was doing is he used an algorithm, a process for achieving something, right? Now, if instead I'd ask you to look up a name, that would be a little easier, right? And in fact, if you don't mind passing it back. I actually have a cupboard full of them. All my colleagues know that I like these things. So, but if I was looking up, say, my name in here, Bell, then one algorithm or a different process I could use, well, I could use my friend's algorithm, right? I could just start by going, well, it's not AA, and it's not Alfred, and it's not Alga, and so on, and go through the whole thing. Would I find it?
Yeah.
How long would it take?
Ages.
Ages? Probably not Sunday afternoon because my name comes early in the alphabet, but if I wasn't so fortunate, then I would be there for a very long time. So that algorithm works, but it's not a good one. And so the algorithm I'm going to use is to, it's something that's referred to as divide and conquer. I'm going to start in the middle where I happen to get Mannix as the name. So is Bell on the left-hand side or the right-hand side? There, cool. So, for kids that haven't seen this before, I just say, this is how they work. And saves me having to worry about being invited back. So, okay, now I'm going to divide in half. So I've got Fitchett, left or right?
Left.
Yeah. So you're making a binary decision, and in fact this particular algorithm is called a binary search because I'm just dividing my problem in half. Bunce, left or right?
Left.
And, well, Bev Knockett, left or right? Right. Now, you don't actually have to, I won't bore you by going right down to the details, but in fact, we can work it out without having to rip up the phone book. There's about 512 pages in the Christchurch phone book, so the first time I ripped it in half, how big was my problem now? 256 pages, yeah. Some of you will be going, this is a bit of a setup, these numbers, but that's all right. Next time I ripped it in half, I had 128 pages, then 32s, and so on. Yeah, that's what you're going to say. So how many rips would I have made before I actually got down to the one page that I was looking for? Yeah, depending how you count it, it's about 9, okay? Now that's a lot better than what I presented you with, and it was because I had a different organisation of the data, okay? And by the way, this is exactly, so what we've covered probably 20% of one of the achievement standards for year 11 on searching and sorting, okay? I made you do the hard searching algorithm, I did the easy searching algorithm. We're now reasoning about how long it would take, just about there. Now, suppose instead of the Otautahi phone book, we go to Tamaki Makaurau, say it's got about 1,024 pages. It took me 9 rips for Otautahi. How many for Auckland? 10, because the first rip got it down to that size. Twice as big, one more step. That's pretty cool. If my friend had lived in Auckland, he would have been going till Tuesday, right? Twice as long. So this is a good algorithm. And in fact, this is a picture. Someone printed all of the featured articles in Wikipedia. So that's what Wikipedia looks like if you print the main articles. Actually, it's only a fraction of them. It was more of an art installation than an actual useful thing. But the how long would it take to search those 5,000 pages? First rip would get it down to 2,500 pages. The next rip 1,250. The next rip 625. You're just about down to the Christchurch phone book, right? Yeah. So in actual fact, it works out about 13 rips. If you printed all of Wikipedia, because you had too much time on your hands, it would be about a library shelf full of information, depending on how big your library shelves are, which is about 1 million pages. It keeps changing. How many rips do you think it would take to tear Wikipedia in half and half again until you found what you're looking for? 20? Yeah. After 10 rips, we're down to about 1,000, and 10 more rips will get you down to 1. So, yeah, just 20 rips. And you don't actually have to rip it, okay, just make sure you know that. Now, suppose Wikipedia grew one day and it ended up with 1,000 million pages in it, which would actually stretch from Christchurch to Oxford, for those of you who know your way around Canterbury. And so that's about 50 kilometres. It would only take 30 rips to find something in my 1,000 million page book. And that's physically, right? I mean, you can see that. If you had to do it, you could try it, and after a while you'd go, oh, I'll just calculate it, right? And if it were to be a million pages, it would actually reach to the other Oxford and back again, it's actually about 40,000 Ks, but it would take 40 rips to find one thing in a million pages, or 40 lookups, 40 operations, 40 computations. And the computation is look at something and make a comparison. That turns out to be one of the fundamental things that defines what computation is, the ability to look at something and say, is it bigger or smaller? Is it earlier or later, or is it the same? Okay. So who searches a million pages? Yeah, Google. So probably most of you in the last hour, you know. And how long did it take? Well, there wasn't someone at Google ripping up books in half and things like that. It was just a computer doing those 40 operations and going, yep, here it is. If we had used my friend's algorithm, then Google would have done a million operations, or might have been lucky and done half of that, which would probably take a few months. And actually, back in the 1990s, that would have been pretty cool. I'll type in a query, and in a few months I'll get an email with everything in the world that matches what I was looking for, okay? Some of us have experienced that. But these days, that's totally not cool. And so we're making the user wait. At which point I want to introduce a student I will call Peter, which is not his real name, who we ran a code club for kids, and Peter would have been about 12. And we're teaching him how to write programs. And I went and looked at one of his programs. It was kind of working, but at the end of it, he had these 2 lines of code. Now, the first one, sleep 10, means wait for 10 seconds. And the next one is, it puts the result on the screen. And I said to him, well, why does it wait 10 seconds before it puts the result up? And some of the teachers will anticipate the answer, because that will really annoy the user. Actually, I was talking about this with a teacher friend last night, and she said a lot of their 12-year-oldish boys love doing that. As soon as they find the delay command, they just throw it in and hold things up, right? Manaakitanga? So one of the things that we really want to get across is that we write computer programs, but we don't write the programs for computers. We write the programs for? Thank you. And who are good at understanding people? Other people. Teachers are very good at that. Absolutely. But in particular, what's your stereotype of a computer programmer? Well, maybe some of you don't hold that stereotype, but if you talk to parents, if you maybe talk to teenage girls, you'd say, what sort of person makes a good programmer?
A geek.
A geek. Social skills? No. Not so much. Okay.
Hygiene skills.
Hygiene skills. Going with that, the ability to work with others, really enjoy talking and coming up with solutions with other people.
Very intelligent.
Intelligent? Yeah. Okay. What gets the job done? And some of you have probably written programs written by people like Peter. Okay. Now, they don't probably deliberately insert things, but I have heard people like that say things like, well, if they can't use it, they shouldn't be in whatever profession they're in. If they have a problem with that, then there's a dummies book that they can read. Anyone got a dummies book on their shelf or something like that? Yeah, complete idiots books and so on. Because these systems make people feel like complete idiots. The systems, the software that you use that doesn't make you feel like a complete idiot, you don't really notice it. Well, yeah, okay. And we have a technical term for good software. It's called usable. Okay, usability is a huge area. And so when we think about delays, one of the things that a computer scientist needs to know about, and this appears in the level 1 NCA standards, is how the time frame that people work on. And so I'll do a quick experiment on you. I'm going to click my fingers and just point at which finger I click first. Pretty good? Okay, going to bet $10 on it? No. One of them was first, but there's a time period where you can't detect a delay. And there's better, there's some of the links I've got, you've actually got online experiments where you can click on things and go, oh, was that a delay or not, and measure what that time is. You'll notice that sometimes when you flick on a light and you go, oh, that didn't work, and then the light comes on anyway. So it's that amount of time for your brain to go, that didn't work. And has anyone ever sort of clicked or pressed or done something, you go, that didn't work, and you press it again? Yeah. Which often turns it off. Yeah. And so you go, yeah, that didn't work at all. And so eventually you just keep hammering it, and eventually it comes on, right? Yeah. In interface design, we call that the user's model. And you want to get a good model in their head of what's going on, and you can really stuff it up by putting in delays. A delay of, for most people, here's the experiment I did on myself, which is that all the blue ones are where I couldn't tell there was a delay, and the orange ones are where I could. And it's a great graph because it hasn't got any units on it, but that's milliseconds. So, thank you, the science teacher there, I'd say. 100 milliseconds is the limit for nearly everyone, and that's regardless of age and gender and all sorts of things like that, that pretty much everyone on the planet cannot perceive something that happens within 100 milliseconds or a tenth of a second, and if it's more than that, nearly all of us will feel that delay. And so, a computer scientist, their job is to make things happen within that time. And so if I'm using my friend's algorithm to do a search, that's definitely not within that time. If I use the other algorithm, which only does 40 computer operations, and computers do billions of operations per second, then it probably will happen within that time. And the main delay is that if you do a Google search, it has to go all the way to wherever, probably Australia. It's done on a big database there, and the result comes back. So it's actually the network time that's mainly holding you up. Although Google tell you how long they actually spent searching for your result. If you want to look at it, it is more than 0.1 of a second, because there's another time that computer scientists need to know, and that is conversational speed. So a fun experiment for you to... Try this at home. Just randomly put in a 2-second gap when someone's, how was your day? Yeah, great. What were you doing? Went to the PPTA conference. How was it? Yeah, it was fine, actually. Our brains work at about the 1-second gap, and that's the other magic number that we have to aim for with interfaces, is to get it back to the person within 1 second. There's another number, and some of you may be familiar with it. Can you remember the number that I asked you to search for? 385, yeah, 3851024. Well done, but yeah. Now, if at the time I'd said, by the way, later on, if anyone can repeat this number back, I'll give you $10. Then what would you be doing? You'd be memorising it. You'd take it from your short-term memory and put it into your long-term memory. Short-term memory, on average for people, is about 8 seconds. We usually just say 10 because then those three numbers are nice and simple. Tenth of a second, 1 second, 10 seconds. And actually, it varies a lot. Some people, it's more like 20 seconds. And there are some people that if they hear something once, they just remember it, which is pretty cool. Not terribly useful in this case, but so I'm not offering $10, but... Oh, okay. There you go. Yeah. And so things that take more than 10 seconds to respond, we need to put up a sign or something that says, this is how long I'm going to take, a progress bar to give people a sense of, purpose and closure, and whether they've got time to have a coffee before they come back, or whether it's just about to do all those sort of things. Programming those things in is not trivial. You need to know about, like anyone could write my friend's algorithm and just go through everything looking for it. And this applies to so many things that happen in apps, that you can make them slow just by using the wrong algorithm. Now, I haven't even defined what an algorithm is, but you get the idea. And incidentally, quite often people say, can you just give us definitions of all these words in your algorithm and all that sort of thing? It doesn't really work. I challenge you to try and define what a car is. Actually, do it. Define a car to your neighbour. See if anyone's kind of really good at waterproof explanation of a car. Okay, so how are we going? Okay, thank you. Okay. So, was anyone really satisfied with their neighbour's description of a car? No. You probably eventually get there with a bit of legalese and all sorts of other disclaimers and things. But the thing is that just defining it often doesn't really help, but doing it does. And that's why I started by ripping up a phone book, because we did an algorithm. I referred to it as an algorithm, and people kind of went, oh yeah, whatever, that must be an algorithm. That's how we teach kids what a car is, right? You say, oh, there's a car, hop in the car, watch out for the car, that sort of thing. And after yeah. So, computer science is manaakitanga. I'm going to try out a slightly different algorithm with you, and this is a game that I will look for. Here it is. So underneath these boxes are some numbers. I don't know what's under there because it generates a different set every time. And by the way, the link to all of this stuff is going to be in that doc that I talked about. But I'm going to click on it, and there's scores for some game, and we want to work out what's the high score. That's a really common problem that we need to solve, and I'm going to get you to see if you can work it out. So the number under here is 205, 228, 279, 269, 121, 152, 231, 114, 110, 103, 250. What was the largest of all those numbers? Cool. How many numbers did you have to remember while I was doing that? One. How would you describe that number? The highest? The highest so far. Brilliant. If you were writing a program to do that and you called it highest, then I'd say, oh, it's not a great description because it's not the highest, something else might be. But the highest so far is a brilliant description because at the beginning, what's the highest so far? Well, the first one is always going to be the highest so far, so just remember it, right? That's the algorithm. What decision did you make when I put the 228 up? A comparison. One of the 6 key elements of computation, okay? And then I repeated that for as many boxes as there were. That's one of the other 6 key elements, is the ability to repeat things as many times as you need. In this case, 11 times, because I'm getting people to do it. But if there had been 1 million, computer would go, yeah, sure, I'll do it 1 million times, whatever, you know. And so that's where we let the computer start taking over. And you've got the highest so far that you're remembering. Writing programs is, I've said you're not writing for a computer, you're writing it for a person, but you're also writing it for the next programmer who's going to try and make sense of what you've written. And so if I say, can you give me a 2 or 3 word description of exactly what that value is that you're storing, that's absolutely crucial so that the next person comes along and they see highest so far and they go, oh, I know exactly what you're doing with this. And so writing programs actually involves really good literary skills, the ability to say something in a few words that makes complete sense. Okay? And maybe even putting a little note on explaining what you're doing, things like that, that someone looks at and they go, know what you're doing, thank you. That was also what made that an algorithm, or what made it computation, is I only used those same operations, right? Comparing 2 things and deciding something about them. So, just out of interest, there's a program that implements exactly what you just did. And I've chosen, 12-year-old boy variable names, if you don't mind me saying that. And sometimes some teachers will have seen worse variable names than those. It works, it does exactly the right thing, okay? But here is exactly the same program, but I've used a few literary skills to actually, I haven't just typed HS, I've said that the name of this is working out the highest score, and I chose highest so far as the name of the thing that's keeping track of it. And I said, look, the very first thing, we'll call that the highest so far, and here's a loop that just says, if it's more than the highest so far, then we'll make that the highest so far instead. What I'm trying to get across is that is actually quite a complicated algorithm. It's quite a complicated program, and I certainly wouldn't expect that to make a lot of sense straight off the bat. But can you see that knowing the algorithm is the first step, which you pretty much all invented for me, and then you coded it into something that would make sense, and hopefully you use some good skills so that it would actually make sense to the next person who looked at it. In fact, you don't even need to be able to read code. You can look at this and it's got enough information there to make sense of what it's doing. And so in fact, a guy called Alan Blackwell once pointed out that many of the skills of a professional programmer are related to social context rather than a technical one. Now, that's not to say that you don't need those technical skills, but the people who are most employable are the ones with the social skills. But you can work in a group, you can communicate, all those kind of things, you can work out what the user wants, and you can manaki the user. That on its own, not enough, but combine that with the technical skills, which are very learnable, then you end up with very employable people. If you go back to our stereotypes, and if you look at the numbers of people that are doing computer science, digital technologies, who's missing? Women. About 20%, used to be 10%, so we're making some progress there. In fact, one of the cool things is that when this went into the NCA, 2011, when that cohort of students came through at our university, the number of women that enrolled doubled. Wow. And the year after it doubled again. Now, when you say well, went from single digits to double digits, but and double digits to big double digits. But that's the thing is, it's a bit like what I was saying with definitions, is that for kids to have a vision of what they can do, just do it. And one of my biggest motivators is nearly every woman who I've come across who's been working in this, and I often get them to come along to talks and talk about what they like about their job and all that sort of thing, is that I've only ever found one who got in on purpose. They all got in by accident. So one of our best students ever actually, in her words, hated computer science with a passion all through her teenage years. Didn't know what it was, but she hated it with a passion. And because basically social suicide to hang out with those kind of people. But then she acquired a boyfriend doing computer science and sat with him in classes and went, this is really interesting, and enrolled. And I first met her because I had to give out the top prize for that year to her. And she'd enrolled as a journalism student, and she just nailed this stuff, because who can communicate? Journalism students. And so... Exactly. I'll let you draw your own conclusions. And there's one other group that are quite good at Manaki. They've grown up with it. They've grown up working in groups. Yeah. You put it that way, yeah. But our Māori Pacifica friends, are so good at this stuff. And boy, when they get into the software industry, do they nail it. It's about creativity and working with people and so on. But they don't see themselves there necessarily. And so for me, this whole purpose is to let them see themselves there. I'll introduce you to one more student, Hannah. She joined the club, and she was in the same club as Peter, actually. And in fact, I remember on one occasion where I don't know if it was Peter, but one boy said, I've nailed it, I've done it. And I went and looked and said, yeah, it's 80% working, there's a few things to work on. And went over to Hannah, and she said, oh, this is terrible, I just don't get it. And you could, basically the subtext was, I'm not doing as well as those boys over there who have nailed it, who hadn't, right? She had got it about 98% working, and she knew the 2% she hadn't achieved. And so she could produce a 100% thing. She knew how to do that. The boys were going, oh, it's working, forget anyone being able to use it. It's, Now, I am stereotyping a bit. There are amazing boys who end up as programmers. There are some girls who, it's not their thing, okay? And that's absolutely fine. But with Hannah, what we did is we actually set up a girls' club. Her mum emailed me and said, oh, she's pulling out, it's just not her thing. And I said, she's really good at it. And so we set up this girls' club, came along, and these girls just totally took off because they weren't working with people who were saying, I'm better than you, I fit your preconception of who's going to do well at this. So we end up with this thing called computational thinking in the curriculum. And it's now from year 1 to 13, though it's probably more about year 4, 5 that kids can really start doing stuff. The digital technologies, there's 2 parts of the technology curriculum there, computational thinking and designing and developing digital outcomes. Now, my interest as a computer scientist is the computational thinking, which is everything that we've just been doing. It's what is computation? Well, it's comparing things, it's repeating things, and so on. Designing and developing digital outcomes, really important. Nearly everyone's going to have to use a computer for what they're doing. They're going to have to learn how to learn on computers, all that sort of stuff. But generally, people can figure out how to do that. And but computational thinking, it's just a qualitatively different thing. Does anyone know who this guy is? He's just appeared on the £50 banknote. Alan Turing. Yeah, pretty cool, eh? And the really, well, not that I've got one, but the cool thing on this banknote is, although nomenclature up in the top left there, is his proof about what computation is. So you know how I said it was 6 things? That's essentially his original proof in the 1940s, saying, we've just invented this thing called computation. It seems to basically have these 6 elements. He didn't quite he articulated it like that, actually, so it didn't always make a lot of sense. But if he turned up here today and saw a tablet or a digital watch or a Fitbit or something like that, he'd be going, it's just got the same elements in it. It's doing the same kind of computation, the same 6 things. It's just way smaller and faster and so on. And what are those 6 things? So we've done most of them, but the first one is sequence, the ability to, so computers can follow instructions one after the other, okay? And so to program, you need to know how to put things in a sequence. So, what was the first thing you did when I asked you to find the largest number? Well, you say that the first thing is the largest so far, okay? And then after that, you do other things. They don't all happen at the same time. The next one is selection, which is what you're doing all the time, comparing 2 values and saying, is it bigger, is it smaller, whatever. The third one is the ability to iterate or repeat a number of times. Fourth one is the ability to store something, which I was making you do, remember that single number that was the largest so far. And without input and output, they're not much use, because it just sits there doing stuff. So you need to be able to put values into it, which might be a camera, it might be a mouse, it might be all sorts of things. Even shaking a phone is input to it, right? Tapping, things like that. They're just input. And output. So they haven't changed. And part of the reason I want to really emphasise this is that people worry that this whole curriculum, it's going to change every couple of years as people invent new stuff. It doesn't. The way it looks does. Going back to the pipe organ, if J.S. Bach turned up today, any music teachers here? Yes, cool, right. If Bach turned up, would he turn up in the music department and go, I have no idea what all this stuff is? No. He'd go, oh, you call this thing a synthesizer, I wonder, I can think of some cool stuff to do with that. That Spanish guitar thing there, it's interesting, yeah. And so, it's the same with computation. So there are some fundamental things that don't change. My friend's algorithm was bad 30 years ago and it's bad today. If a computer runs it, it will be burning up energy that it just doesn't need to. And, well, one thing you don't want to do is burn energy on one of these things, because basically you end up with a flat battery at lunchtime, right? So in the curriculum, the computational thinking part is a series of progress outcomes. I can't really unpack them too much, but number 5 is the Year 10 one, and it says students will know about inputs, outputs, sequence, selection, variables, and iteration. Who came up with that idea? Alan Turing. Oh, by the way, if you like Benedict Cumberbatch, he did a movie about Alan Turing. Yeah. Oh, now you know who he is, yeah, right. So it's, for a lot of people reading this for the first time, they go, whoa, that's just a whole lot of jargon and so on. It's just what you were doing before, and it's not there randomly, it's there because that's how everything works. I mean, there's a couple of other things, that last word there, or the last couple of words, HCI, heuristics, human-computer interaction. That's all about what we were doing before. How do you monarchy someone? What's this time frame in which they work? Has to, and there's a whole lot of known stuff, and all of this is available for kids in a form that they can access and play with and try out themselves. And it's really just to get them in that frame of mind. In terms of seeing themselves in IT, there's also there's a bunch of websites now. A lot of people have put these together, but if you're interested, for example, in women in IT, there's a site called Chic and Code, and it's got stories of a whole lot of women who are really into coding in New Zealand, okay, who have made a difference. And there's any number, I'll put up a few more links to things like that. One quote that I think really nailed it, and it's from 2001, is that well-known psychologist Albert Bandura. He did all the stuff on self-efficacy and that sort of thing. And when he was talking about that, he was saying everyday life is increasingly regulated by complex technologies that most people neither understand nor believe they can do much to influence. And I think our job is just to turn that around. Our students are in a world regulated by complex technologies that they kind of understand. I mean, after today, do you kind of get how Google might be able to search billions of things really quickly? And can influence. If they've got an idea for an app, then they've actually perhaps had the experience of implementing something and seeing how that plays out when you do that. In terms, and then digital technologies and programming, it's a little bit like mathematics or literacy. It applies to everything. My wife is a music teacher and in an intermediate school, and some of the kids came over to the music block, and I can't remember exactly how we did, but she said, let's do some programming to program some music up using Scratch, the programming language Scratch. And their reaction was very much, but no, Scratch is what we do in the tech blog, and programming has nothing to do with music, right? And you say, well, when you're learning, these are like virtuoso pianists and music geeks and all that sort of thing. Where do you listen to music? Oh, well, Spotify and YouTube. It's like, anything digital going on there? And, you know, electric pianos and synthesizers and electric guitars all have computation in them. You know, even a simple guitar amp now will often have a whole lot of effects, which is just a computation that's going on. It's going, is it time, is it time? Yes, play that loop again, you know, things like that. All of that, all those things that Ed Sheeran is doing is just those 6 things happening inside a looping box, right? But put together in a way that makes sense musically by people who understand what musicians are after. And maybe one of your kids will invent the next musical instrument or the next musical effect or the next practice software that helps them to really improve their technique or something like that. It applies to so many different things. I thought, just in the spirit of that each talk today seems to have to include something about COVID. No, too soon? So this is a program, I just looked at programs that kids had written around COVID, and this is a simulation. I'll just run it. And so the green dots are uninfected people, the purple dots are vaccinated people, and the red dots are infected people. And they've just written a simulation where the red dots move around, and if they bump into a green dot, they're infected, and purple dot, they don't. Very simple model of how infection might spread, but also quite a scary one when you look at it like that. The variable that they can change up here is how many people are non-vaccinated. Now, it's actually a terrible interface because it says non-vaccinated chance. I had to read the program to figure out what that means. It actually means, if you put it on 2, it means there's 1 chance in 2 that someone's non-vaccinated. So I'll put this on 2 and start it again. So this is where if every second person gets vaccinated, then the red dots are sort of having more trouble. And then you can, what's more interesting actually is really just to look at the program, and with this we can look inside. Might look a bit scary, but here it is. This is when a dot gets started up, its vaccination state its value gets set to 0. Might have been nicer if they'd called it not vaccinated rather than 0, but it's okay. I'd understand it better. And then it picks a random number between 1 and whatever that chance is, like 2. So a random number between 1 and 2 if it's 1. And here's our selection, our if statement. If it picked a 1, then it basically changes its colour, okay, and starts deciding about whether it's going to recover from the infection. But this is pretty much the whole program you can see on here, and I appreciate that it's almost impossible to read at that distance, but I can make it a bit bigger and you can't see it all. But the thing is that, excuse me, using the tools of computation, there's our selection, our if statement to say, you know, did I choose it as vaccinated? There's a couple of others. There's an if statement here saying if it's touching a red thing, then it becomes infected, right? Things like that. And that's the whole simulation. Now, it's not terribly accurate because it doesn't have the idea that there's still, you know, what about distancing? And some kids have done simulations where they say, well, what if we change it that none of these dots go closer than 1 metre, and that reduces the chances of infection, all that sort of stuff. The point I'm trying to make is that it's a tool that enables us to do all sorts of things that are relevant to other disciplines. And if you think of your own discipline, if it's not digital technologies, where does digital come into it? I was talking once to someone who was doing drama, and said, well, I'm doing drama, obviously there's nothing digital there. Exactly. I think any sentence starting with obvious is kind of a bit of a red rag for me, but it's... so, yeah, lighting, scripts, direction, sound, special effects, and let alone things like costumes, digital costumes, things like that. Yeah. So why do we call it digital? Basically, I won't unpack this too much, but it's just about numbers. It's about digital. And in fact, the Te Reo version makes that clearer. So mati, or mati, fingers. Mati is a digit. And hiko, machine, hiko, or electricity. Yeah. So it basically says electric digits. Okay. All of these things are just a bunch of digits, and we haven't had time to get into that, but those 6 operations are being done on digits. You can copy digits. One thing kids do like, and in fact computers only work with 2 digits because it's so much easier to, we normally have 10 digits, right? 0 to 9. With 2 digits, 0 and 1, the times table, 0 times 0, 0, 0 times 1, 0, 1 times 0, 0, 1 times 1, that's the entire times table. Yeah, I don't think I've ever done that with kids and they haven't asked to switch to that. But you can also see why it's so easy to build things that only work with 2 digits. It's a bit of a, there's a bit of weirdness, but it's actually quite easy to get kids interacting with that idea that we can represent anything using just 2 digits. Every photo, every Spotify file that you're listening to, every game that you play, so the programs themselves are stored using digits. I'm aware that we're probably just about out of time, and I'd like to get a bit of time for questions. For those of you who have been following ERO, they have been looking at how schools are doing, and I'll put up a few links to that. But back in about 2 years ago, they found that I think it was 7% of schools were ready for this new curriculum. But then, of course, in 2019, we were going to have lots of time for that, except there was a few industrial issues then. And so in 2020, we were going to have lots of time for that, except then there was another issue that came up. So we're kind of at the point where, not surprisingly, a lot of schools are still getting off the ground. And this report is kind of cool because it's called On Your Marks, Get Set, Go. And it's just a study of 3 lots of schools. On your marks, as in, we've heard of it, we should really get onto this. 1 or 2 people here might understand it. Get set as, we're actively getting into this, we see the value of it, and we've got people working on it. And go as, well, we've kind of got the curriculum going. It is going to take a few years. I mean, anytime I teach something new, it takes me at least 3 years until I realise what I'm teaching. Usually no students are harmed during those few years, but, is it like that for others? You sort of, you teach something and after a while you go, oh, now I get what that's about. Yeah. So, have a look at that report. But, just to conclude, why are we teaching this stuff? It's kind of so students can know coding because that is a string to their bow in the same way that it's really good for them to know numeracy and literacy and social skills and all sorts of other things. So we're developing skill in all those different areas. We're developing their vocabulary so that they can actually work in those spaces. Even if they don't become experts in it, they'll probably be making decisions about those things. We have to make judgments about genetic modification, about vaccines. I mean, who knows all the ins and outs of biology around vaccines? Do you get your information from people you trust, or do you kind of understand how it works? And it's going to be the same with things like AI and information in our digital future. Self-efficacy, I think, is a really big one. That's the one I'm sort of passionate about, as our students develop that ability to see themselves there. And you have to do it to be it, as some people say. Diversity is so important. Employers are just hanging out for diverse teams. You make more money off diverse teams, just to be blunt. They produce products that lots more people want to buy and that have much higher value. But I think the key thing is we just want to give our students a vision for what they might be or what they might not be, but to make a judgment based on what it really is. So that's what I really wanted to share today, and hopefully I've got a little bit of time for questions. Yeah, thank you very much for your time. All right, we have a microphone.
Yes, we do have a few questions here, and I'm going to let the people who have got the questions up here address them. So, Eliza, are you?
Kia ora, I'm Eliza Gartlett from Wellington College and also chair at Te Aroha Primary School where my children go, so I've got a lot of interest from both perspectives. My question was, are humans still going to be programming computers in 10, 20 or 50 years, or are they going to be programming themselves?
That's an awesome question. To cut to the chase, humans will be needed to program them. There's a couple of, so there's some very scientific reasons. If we go back to what the definition of computation is, it has been proven that you cannot write a computational thing that can do certain things that are needed for programming. Like, it just will never happen. I mean, that might seem hard to believe, but there are some things that you cannot do. And amongst them, so programming isn't so much writing the code, it's actually debugging it and that. But also the really big part of it is, what are we going to build? Who are we going to build it for? What are their feelings? What are their needs? What are their abilities and so on? Now, there is an awful lot of automation of this, and so we can be way more productive. The computers, and that's one thing computer scientists do. They build tools using computer science to help them do their things better. But no, humans are needed for that. But I think more and more the actual coding side of it might get less and less. Already coding is about 20% of a person's job. So there are lots of companies around here that have 300 employees, zero, Christchurch, there's about 200 companies with multiple, lots of employees, most of them with dozens or hundreds. They spend about 20% of their time coding. So even if computers did all the coding, they could take Fridays off.
Thank you. And now I'm going to hand this to Paul.
Kia ora, thanks Bernie. Thank you for your talk, Tim. I suspect that if I had had a teacher like you who was so passionate about computing back in the day, maybe my life would have gone differently. And maybe earning more as well, I think. Sometimes you hear about developments in technology that move away from a binary system, which I understand does have some limitations, which you kind of touched on but didn't go in depth on. So my question is, do you believe that quantum computing or other similar developments in technology could fundamentally change the nature of Turing's 6 laws in the future?
Awesome questions. Again, short answer is they will change it, but they will build on what we know. And so you can't sort of say, I'll skip all that stuff. And then, so quantum computing in particular is a really interesting thing on the horizon. It kind of works, but kind of doesn't. And we don't know if it really will fulfill all the promise that it's got. But with the current computers, we use bits, binary digits. With quantum computing, we use qubits, quantum binary digits. So like that multiplication table we just did, still applies to qubits. It's just in a quantum way. So, and I think it's a little bit like going from Newtonian physics to Einsteinian physics, if that makes sense. So, in Newtonian physics, if you travel for an hour at 20 kilometres an hour, you travel 20 kilometres. In Einstein physics, if you do that, you travel 19.9999999 kilometres. Doesn't mean we don't teach Einstein's view of things. We just eventually say, we can do a little bit more than what we've told you, but we're going to build on that. That's the short answer. There will be more to learn. Kids can already. We've written algorithms for quantum computers that don't exist because we know what they'll do. In the same way, you gave me an algorithm, but maybe some of you can't program, but you still know what the algorithm will be. Even if computers didn't exist, you would have come up with that algorithm. And so it's just more and more of the same. Yeah.
Fabulous. And then finally, I think we'll just do Grant. Where are you, Grant?
Thanks, Aaron.
Got it.
Just really, I've been in this weird world of teaching digital and social sciences all the teaching career. So I went through the whole computer science board guide with you guys early on, Google based. But what I continually do is try and integrate it into the social science. And I don't know whether it makes any sense, but have you had any thoughts about the new digital curriculum, how it can be integrated across curriculum,
Yeah.
especially Friday, obviously, because it's the key subject, but really any subject.
Yeah. Yeah. I've had a few ideas, but generally the way I find works is to have a corridor with someone in that area, and generally we'll come up with 20 ideas, and then 16 of them we never speak of again, and find those things that will really engage kids. And so because I happen to live with a music teacher, that comes up a lot, and so I've got a lot of things in that area. In fact, quick advertisement, there's a joint Tens Mensa conference next holidays that hasn't been advertised yet on exactly that intersection of music and tech. There's also, we actually have a thing going on at the moment that I'm bunking from in Otatahi, where we've brought in people from all around the country who are putting together resources that are integrated like that. And so those conversations are happening, and by tonight they have to have them up online. So, and I'll put a link into that in that doc. So I think each expert in those areas needs to have those conversations and see what they can come up with. Enough said. Right. Yeah.
So with that, I think, if you have got further questions, please feel free to come and see Tim later. I'm sure he's going to be around during lunch.
Yeah, I'm only around for a little while because I have to
Okay.
get back to these people who are busy creating stuff. But come and grab me now if you've got a question. I'd love to do it.
Well, I'll just like to finish with, your presentation has certainly enabled us to make sense of digital, or better sense of digital technology. You brought to our attention very quickly the reality of technology and its glitches, computer technology, hence Manaki. You've touched on binary decisions. That fabulous example with the phone book, I'm sure lots of people are going to be trying that experiment. And this means of searching was, as you suggested, an algorithm, those 9 rips in the Christchurch phone book. Wow. You also taught us the effect of a pregnant pause. Your visual graphics, your wonderful humour, your overall message have been relatable and most engaging. And with that, we have a small gift for you. Thank you so much.
Thank you.